produce these proteins in different forms, and we call them isoforms. And for now, let's just assume isoforms can be like inactive or active forms of something. Iso means same form compound that we're studying, but let's just think isoforms like a lot of times you can produce something that's inactive just so it's there ready to work, and you don't have to make it, right? You just need to turn it on. And that turning on involves activating it, right? Some things, the activation requires taking the protein that was produced and maybe breaking it in half. That's called proteolytic activation. Insulin is a common example of this one here. We produce what's called proinsulin, which is an inactive form of insulin that circulates around, and only under certain conditions does it become active, and the activation requires breaking it in half and having it join in a different way. So that's an example. Cofactors. Cofactors are things that we have to add to the protein in order for it to work. Right? So we add something else, so this is extra. A lot of times these cofactors, these can just be ions. So sometimes without an ion, it's inactive. With an ion, it's active. We'll see, like, what's coming to my mind right now real quickly is like calcium. Calcium often serves as an activator to certain things as a cofactor. It binds to a protein and then turns the protein on. And we'll see where that goes. That's true in muscle contraction, especially smooth muscle contraction. So we'll look at that and some examples of that there. A lot of metal ions, magnesium, calcium, those things are all serve as cofactors a lot of times to these things. And what they do is they alter the local environment here because they're ions, they're charged. If you start sticking, positively charged ions on this thing, guess what? Its shape's going to change. And if its shape changes, it's going to affect the affinity. So that's how those cofactors work, is by affecting, overall shape of a protein. I already mentioned about modulators here. Modulators can be antagonistic, so they can turn things down, or protagonistic, they can enhance things. A lot of times these things, the ones that down-regulate or turn them off, we call them competitive modulators or competitive inhibitors because they actually bind to the active site. So one way to turn off this protein is by having something sit down right here, right? Cover up that active site. That would be called competitive inhibition because it's competing for the active site. If it was something else that binds over here and then just changes the shape, then that would be non-competitive, right? Because it's not competing for the active site. Now these things like this that bind other than the active site to either turn on or turn off or increase or decrease the affinity are called allosteric modulators. Now allosteric, the name just tells you, allo means other, steric, shapes. So these are compounds that make this thing have other shapes. It's allosteric, right? It makes it have other shapes. So an allosteric modulator is something that binds to the protein, makes it change shape, and either increases or decreases the affinity, whether it's a protagonist or an antagonist. Right? If it's antagonist, it decreases the affinity. If protagonist, it would increase the affinity. And then there are numerous... Everybody okay? Am I going too fast? I don't know. I mean, it's a lot of info, but it's kind of... It should kind of make sense as you sit there and listen to it. You may not remember everything, but it should kind of be. The other thing that affects, and we talked about that with these chaperone proteins here, the other thing that affects affinity is our physical factors of the environment. And there's two physical factors that are really important for us, and they're temperature and pH. Now, under homeostasis, if we are in homeostasis, these are not a problem, right? Because we're maintaining a proper temperature and we're maintaining a proper pH. So they're constant. Well, constant is not a good word. they're optimal under homeostasis. So we will get proper folding of the protein that gives us the proper affinity, and we'll get the proper interaction. If we alter temperature or we alter pH, we can affect the folding. So those are two that are important. We'll look at some graphs of them here in a minute, and I'll show you. The other thing is that can affect this interaction that's part of, I guess, the physical environment, is the concentration of the ligand. If you change the concentration of the ligand, you'll get more or less of this. So let's say, for example, so here the amount of protein is constant, and we're increasing the amount of this ligand, preferred ligand. As this concentration goes up, the interaction goes up. Does that make sense? To a point though, right? Until what? Saturation, you run out of protein. So if we were to look at saturation here in kind of a graph, here, and we're looking at the interaction here as a function of the concentration of, what did I say, ligand? Concentration of the ligand here, like that. What would the shape of this graph look like?
It would peak and plateau.
Yeah, it would increase, and then it has to plateau. And at this point where it plateaus, right there, that is the maximum effect. Whatever it is we're talking about, if it's an enzyme, if this is an enzyme catalyst, if this protein's an enzyme, that would be the maximum rate that the reaction could occur at. Right, would be right there. And it occurs at this point right here, and that point right there is saturation. So at that point, all of the proteins are bound to a ligand, and what determines the effect is just how quickly each individual protein works. That's the maximal rate. So that would have an effect to a point, right? If I want to get more of the interaction occurring, I add more protein. Less of the interaction occurring, less protein. And obviously there's a cap, a maximum interaction that's due to that. Is that okay? That makes sense? The other thing that affects it also is the concentration of the protein. So here, if we were to do a comparable thing here,